So we've already done a little work with two variable systems. We'll just review those real quick and then jump into three variable systems. So in this two variable system case, we've got a couple of options to solve them. We know from Algebra 1 we can do a graphing method, which is really inefficient, and then we can do a substitution if it's set up in this format where we have one variable already solved for another. That's probably one of the easiest ways to deal with that. So what we're going to do in the substitution again is we'll take this quantity of negative x plus 3 and substitute it in for y, and then solve for x. So we've got 2x minus the quantity of negative x plus 3 is equal to negative 9. Distribute through. Combine like terms. Isolate that variable. And divide. Once we're done, we take the value of x, shove it back in to one of our original problems. It doesn't matter, either one will work. So we have y equals opposite of negative 2 plus 3 or 5. You can give me the answer in this way. Some teachers prefer the ordered pair. Oops. The ordered pair. I personally don't care. It's kind of up to you guys. So negative 2, 5 will get that done. And again, that basically is an example of two lines intersecting at a point. So in a case like this, rather than substituting, which we could do because we could set this equal to 4x and then substitute the 4x out in this problem, we can use elimination where we have opposites here and add these up. In this case, the x's will go away and we end up with y equaling 10, and then we substitute that 10 back into either of the two equations and solve. So we end up with 56 is equal to 4x, and x equals 14. Again, we can state the two solutions or put it in an ordered pair like so. So in this case, you'll notice we have no matching terms in terms of variables and coefficients. So what we can do is still do elimination, but in this case we're going to have to multiply either one or both of the equations by a constant in order to match the variables in terms of coefficients. So I'll multiply this top equation by 5 and the bottom equation by 2, thus being able to get rid of the y's in the end. So I have 25x, negative 10y, and 5, and 8x, and positive 10y, and 94. Thus, I have 33x, 99, and x is equal to 3. Substitute back into either equation. I'll have 5 times 3 minus 2y is equal to 1. Bring that over, get negative 14 is equal to negative 2y, and y is equal to 7. So 3, 7 would be my coordinate point. So we'll also have some application problems, typically head spin or headwind, tailwind problems. Also, you'll see like current problems, upstream and downstream, so on and so forth. Remember, headwind opposes travel. Okay, it pushes against you, whereas tailwind helps you. That's going to be important in this problem. So we know that in a headwind, it's going to fly 1,800 miles between two cities in 3 hours and 36 minutes. On the return flight, in which case they're going to now have a tailwind. It only takes 3 hours. They want to find the ground speed and the wind speed, and assuming that those two remain constant. So not typically realistic problem, but you get the idea. So you've got a couple options here. I'm always a fan of filling in the time if I can, making an expression for the rate, and then multiplying to get the distance. So in this case, I'm going to label, and I'll have this with the headwind and this with the tailwind, just so we know. 3 hours and 36 minutes. I'm going to put that all in terms of hours. So that's 3 and what is that? 3/5 of an hour. And then the other is 3 hours. So my rate is made up of the plane speed and the headwind and the plane speed and the tailwind. So in this case, here's the plane, and we're going to subtract off the wind because it's going to oppose our plane speed. And then here's the plane plus the wind. And then, like I said earlier, we're going to multiply these across. We'll call this 18/5 P minus W. And this is 3 P plus W. And now we can take and write two equations relative to the distance. So I have 18/5 times P minus W is equal to that 1800. And then 3 times P plus W is also equal to that same distance of 1800. And now I just have to solve this system. So I'll multiply by the reciprocal here, get P minus W is equal to 500, I believe. And P plus W is equal to 600. Notice the W's match, so I have 2P equaling 1100. And the plane speed is 550. Plug back in to get the wind speed. I'll go back into here. So this is P plus W is equal to 600 in the end. And then I'll say 550 plus W is equal to 600. And W equals 50 miles an hour. So now we get into a three variable system, and the idea is the same. We want to get rid of one of the variables and then another one of the variables so we can get a singular variable by itself. Typically I will never use substitution in this. I've seen people do it. It gets messy often, and if you're comfortable doing that, go right ahead, but I just wouldn't recommend it. What I typically do on all these is label my problems. So 1, 2, and 3. And then I note in this case it's set up pretty nicely for me because I see opposites all over the place. I'm going to take equation 1 and equation 2 and add them. In so doing, I get 3x plus 2y. The z's are going to go. It's equal to 8. And then I'm going to take equation 1 and equation 3 and add those. And you'll notice I get 5x plus 3y, z's go again, equal to 13. I'll notice that neither of these are going to match, so I'm going to have to do a multiplication on either term. So I will multiply this equation by 3 and multiply this equation by -2. This will give me a 9x plus 6y equals 24. And a negative 10x minus 6y is equal to negative 26. Add these up, I get a negative x is equal to -2, so x equals 2. I'll go back to one of the two variable equations and say that 3 times 2 plus 2y equals 8. 2y is equal to 2. Y is equal to 1. So now I have x and y solved for. I need a z, so I go back into any of those three equations. Say 2 plus 1 minus z equals 7. So negative z is equal to 4, and z equals -4. And if I want to list that triple as a point, so whereas a two-variable system corresponded to the intersection of two lines, a three-variable system is going to represent the intersection of basically three planes in space. That would be, for instance, something you can see visually is like the corner of a room. You have three planes intersecting at a singular point. Let's do another one. In this case, nothing really matches up, so again, I'll label these 1, 2, and 3, and we'll have to do an elimination case and just decide what variable we want to get rid of, and it really doesn't matter which one you choose. I'll just use x because it's close. I'll take -2 times equation 2, add that to equation 1. So I can get rid of the x there. So -2 times equation 2 is going to give me a -2x plus 4y minus 2z equals -16. Equation 1 is 2x plus y plus 3z is equal to, whoops, that's not plus 3z. Oh yeah, it is. Equal to 9. And those go away. This is 5y. This is z. And a -7. So now I'm going to have to get rid of the x variable again. And in this case, I think I'll use 2 and 3. So I'm going to say 4 times equation 2 plus 3. 4 times equation 2 is going to get me 4x minus 8y plus 4z is equal to 32. Then I have -4x plus 3y plus 2z equals -4. Add these up. I'm left with -5y plus 6z is equal to 28. Kind of nice because now I'll notice that this -5y and that 5y match. And in this case we get 7z is equal to 21. Also nice because I get a nice clean answer. 3 is equal to z. Again, plug back into either of these two equations. I'll just use this one over here. So I have -5y plus 6 times 3 is 28. Bring that 18 over. I get 10 is equal to -5y. Y is equal to -2. And then let's finally get x. We'll say x plus 2 times -2 plus z, which is 3, is equal to 8. This is a total of -1. Bring that over. So I have 9 is equal to x. And so 9, -2, and 3 is my ordered triple. So this problem looks very similar to the ones we've already done, except you'll see as we work through it, it ends up quite different. Again, let's label 1, 2, and 3. I'll get rid of the y's in this case, so I'm going to take 1, add it to 2, get 3x, y's go away, 9z is equal to 0, and then I'm going to take 4 times 1, add it to 3, which gives me 4x minus 4y plus 20z equals -8, and then 2x plus 4y minus 2z is equal to 8. you'll notice that I have 6x, I have 18z, and 0. I notice that each of these have a, well, they have a 2 in common. I'm going to use the 2 in common just for fun. I'll divide each of those and get this term. And now I'm noticing, hey, these are the same. If I were to take and multiply by a negative here, you'll notice that they're the same and opposite, and I get a true statement out of it. Now, if you remember back in two variable systems, if I ever had an equation equaling itself, the solution was basically two overlapping lines which were said to have infinitely many solutions that solve that problem. And this is going to be the same situation. So what we have to do now is we have to say, okay, well, what are all the possible solutions in this case? So in order to do that, we have to assign a variable as an answer to one of the equations that we have. So I'm going to state that let A equal x. So therefore, I have 3a plus 9z equals 0. I'm going to solve for z in terms of a. So now I have 3a equals negative 9z, and 1/3 a, the negative type, is equal to z. So now that I know I have x equals a and z equals negative 1/3 a, I can find out what y is equal to. And I'll just use this second equation. So I have 2 times x, and we know x to be a, plus y, plus 4 times z, which we now know is 1/3 of a, and that's equal to 2. So now I've basically got 2a minus 4/3 a plus y is equal to 2. And I can say that y is equal to 2 plus, actually minus, 2 minus 1 1/3 is 2/3, so bring that over, minus 2/3 a. So therefore, what I have is not necessarily a singular triple as a solution, but I have expressions as solutions. So for this problem, I'll have infinitely many solutions such that I can pick any value for x. Y is going to be 2 minus 2/3 of that value I choose, and z will be negative 1/3 of that value I choose. So there's infinitely many triples such that they are all in this relationship. And that's all we got for today.